Welcome to our Introduction to Statistics video. As we embark on a new unit of study, we're going to begin by laying some groundwork to inform our understanding. The main focus of this video and our learning goals for today are largely devoted towards that task. Statistics is the discipline of mathematics that focuses on the collection, interpretation, analysis, and presentation of data. We use statistics to form judgments that help us solve real problems. Many would consider statistics to be one of the more accessible branches of mathematics, but it's also one of the most frequently abused or misunderstood. Statistics provides us with really powerful tools to inform our decision making. However, if statistics is misapplied or it's misunderstood by your audience, it can lead to some really flawed conclusions being reached. These conclusions are usually assigned undue credibility because statistics is what brought them to the table. To that end, we want to make sure that we're embracing the notion of being principled as IB learners when we use and learn about statistics. We want to make sure that we're not misrepresenting things knowingly or unknowingly to a wider audience.
Oh, people can come up with statistics to prove anything, Kent. 40% of all people know that.
I see.
The intention here is not to sow seeds of doubt about statistics. It is a really powerful tool and can inform us with a lot of useful knowledge. However, we need to be very mindful of who's presenting that knowledge to us and how that knowledge was reached. Statistics requires a healthy dose of skepticism and a good base of mathematical understanding so that you can make sure you look at statistical information through a clear lens. The challenging part about statistics is sometimes the ways of knowing that actually inform how we reach statistical knowledge. See, statistics is informed by the intersection of memory, reason, and intuition. Like all mathematics, reason helps us to make logical deductions based on facts. While other areas of mathematics have a very firm foundation based on reason, usually built up by axioms or rules that are used to prove things, statistics also has a dependence on memory. In the realm of statistics, memory is the institutional memory that we have through the collection and analysis of data. Combined, these two ways of knowing help to inform the creation of our statistical models. Now, intuition can help play a part in refining those models, but in a colloquial sense with the broader community, intuition is actually something that impedes our understanding of statistics a lot of the time. People think things work a certain way, and then will often look for data that supports their own innate biases. And so sometimes intuition can be something that helps in our acquisition of knowledge of statistics. Sometimes it can hinder. A noteworthy historical example of intuition trumping the other ways of knowing comes to us from 1948's United States presidential election. The Chicago Daily Tribune famously printed a headline, "Dewey defeats Truman," because the common sentiment at the time suggested that the Republican governor, Thomas Dewey, was very likely to win the presidential election over the Democratic nominee, Harry Truman. And in reality, that wasn't the case. Harry Truman was elected to be president in that election. The lesson here is that intuition may have a place in informing how we come up with statistical models, but we really do need to rely on reason and memory to make sure that those models are valid. Now that we've established some broader conceptual understandings to go along with our study of statistics, let's get down into the fundamental facts and ideas that govern this area of mathematics. To bring us into a more immediate reference frame, I'm going to frame some of the discussions in this lesson around the COVID-19 pandemic. The medical community is currently hard at work analyzing a lot of data related to this pandemic, and it actually will act as a really good framing device for our discussion of these topics. Please note that I have no background in medicine. I'm not an epidemiologist or virologist. I'm mainly looking at the statistical markers in the COVID-19 pandemic and its data analysis. First, let's distinguish between a population and a sample. A population, in statistical terms, is the group being studied as part of a statistical analysis. In most instances, it's usually very difficult to collect data from the entirety of a population. So we end up using a sample, a subset of the population, to make inferences about the population as a whole. So the population is used to help us form a sample, and the sample is used to make judgments about the population. When we talk about the COVID-19 pandemic, the population of this statistical analysis is really everyone. It's a novel virus, meaning that it's new, no one has any immunity or exposure to it before the pandemic started, and so the population that is impacted would be everyone. Our samples tend to come from analyzing cases of people who have contracted the virus, and some of the earliest cases came from cruise ships like the Diamond Princess, which we're going to discuss now. The Diamond Princess had 3,711 passengers and crew on board. After docking near Japan in early February, they conducted 3,063 tests of those individuals on board. This provided a very sizable sample of the population that could be analyzed for different factors about COVID-19 exposure and infection. Of those tests, 634 individuals tested positive for COVID-19. Of those that tested positive, 306 were symptomatic, and the remaining 328 were asymptomatic. Because the cruise ship was isolated, it basically acts as a reliable sample for the whole population because it's almost like a microcosm of the larger community. Experts were able to make a lot of interesting conclusions about infection rate, fatality rate, and the proportion of cases that result in people being asymptomatic. Asymptomatic cases are ones the healthcare community is obviously more worried about because they can spread the virus without actually knowing that they have it. With any statistical analysis, there's always a risk of bias, limitations, or error skewing the model to some degree. Bias is not typically intentional, and it's rarely malicious. It's just something that happens as a result of the complexities of analyzing real-life factors. The study that I was referencing earlier about the Diamond Princess freely admits that one of the limitations of their model is that the earliest tests on the Diamond Princess only targeted symptomatic patients, and so asymptomatic people were overlooked for an extended period of time, and that caused them to underestimate how many people would be asymptomatic. Although the Diamond Princess and other cruise ships like it were viewed as very reliable samples, it's worth noting that the average age of a cruise ship passenger tends to skew a little bit higher, and so it's not a perfectly representative sample of the wider population. Additionally, because the Diamond Princess tests were happening in early February, there wasn't as much known about how COVID-19 susceptibility was correlated with pre-existing conditions, and so this wasn't tested for in this earlier study. Despite these limitations, the model from the Diamond Princess and other cruise ship data was incredibly useful in forming our understanding about how the pandemic progresses. Even though there were limitations in the presence of error, the model just needed to continue to be refined, and this gave a very good launching point. Different types of error can show up in any statistical analysis, and typically you want to minimize them as best as you can. There's sampling error, which is when a characteristic of the sample differs from the population. So on the Diamond Princess, that would be where some of the passengers are tending to skew a bit higher in age than your population as a whole. For measurement error, it's when your measuring tools were inaccurate or lacked precision. In this case, that would likely relate to perhaps something being wrong with the tests that they use for COVID-19. In general, with testing, these are referred to as false negatives, when a testing tool produces a negative result when it should actually produce a positive result. In the realm of COVID-19, there's very little evidence to suggest that the tests aren't working reliably. If anything, data suggesting that there are false negatives are largely based on the next two types of error, coverage error and non-response error. Coverage errors are when your samples aren't large or unbiased enough. And so if you're not conducting a lot of tests, you're not collecting enough data, and that's introducing coverage error into your models that are going to skew your conclusions that you make. Non-response error is introduced when people opt out of the data collection process. In the context of COVID-19, this is likely not an intentional choice that people are making, or at least not a knowing one. Non-response errors are going to crop up because we're not testing people who are asymptomatic. But this is likely not happening because if you're asymptomatic, you're less likely to go into the doctors to get a test done. You would view it as unnecessary, you want to minimize your exposure, and so why would you run the risk of getting a test when you see no reason to do so? Although there's always a risk of error in a statistical model, we tend to eliminate most sources of error as time goes on. More and more data is fed into our models, which helps to refine them, increase their validity, increase their reliability. And at this point, given how much data has been collected about COVID-19, most statistical models that are being run by experts in the healthcare community are really well informed at this point. Now, that's not to say that we have a crystal ball that predicts the future, because statistics doesn't work that way. It's actually more like trying to look at a painting and judge what the painting is about while the artist is painting it. We're still having some of the big picture revealed to us as time goes by and as we're able to collect more and more data. And there's a lot of complexity to that data collection and analysis because this is such a far-reaching issue. Some of the sources of error are even hard to protect against because with COVID-19, you don't really have too much control over what your sample is for your data set. In ideal circumstances, if you were conducting some sort of analysis to answer a statistical question, you would want to have control over how your sample is dictated to make sure your data is really reliable as it comes in. So now we'll talk about different sampling methods you can use when you're doing data collection. The first is just to do simple random sampling. Basically, you have a list of people who could participate in your study, and you just pick random numbers to decide who's going to participate in your sample. In general, you'd expect this to produce an unbiased sample, but it's kind of hard to do in practice because you need essentially a list of everyone in your population to truly do simple random sampling. Another type of sampling that's commonly used, especially if you've ever filled out a Google form or had someone fill out a Google form, is called convenience sampling. This is when basically the person collecting the data pulls in data from people who are in close proximity in one way or another. It may be that they're collecting data from people within their school or people within their class or people who they are able to catch coming into a shopping mall or coming out of a doctor's office. So these people in close proximity become part of the sample. It provides a sample easily for the person collecting the data, hence why it's called convenience sampling. However, it doesn't necessarily guarantee an unbiased sample for your study. A method with a bit more structure to it is systematic sampling, which is basically where you decide on a fixed increment within your population and you pull those people to participate in your sample. So perhaps you decide you're going to survey every fourth person. Those individuals now make up your sample. The challenges to this method are that it's actually a little bit less random than simple random sampling because there's actually a fixed pattern to how you're picking people. So your choices aren't done independently of each other. There's actually an order, a rhyme, or a reason to it, and that loses out on some of the randomness. Some more effective ways for generating a sample would be stratified or quota-based sampling. And that's when you divide your population based on other distinguishing factors that might be relevant to the study, and you use that information to inform your random sample. So if I know how the population breaks down based on certain criteria, and I know the percentage of the overall population that fits into those criteria, that's going to give me a sense of how my sample should be distributed when I randomly generate. So stratified random sampling requires that I uphold those proportions of people within my sample based on those other factors within the population. So I want them represented proportionally based on those characteristics. With stratified sampling, I'll still select those people from their different subgroups randomly. I'll still make those selections completely random. With quota sampling, it's a little bit more a combination of convenience sampling. I'll just reach out to people as I can get a hold of them until I fulfill my quotas for each proportion. To that end, stratified sampling does tend to give a more unbiased sample to work with because quota-based sampling could still introduce some bias based on the convenience aspect of acquiring members of the sample. I'll conclude the video with a quote from a statistician named George E. Box, who said, essentially, all models are wrong, but some are useful. Now, out of context, that might seem like a really negative thing to say about statistics, but the spirit of what he was getting at is the notion that models are generally imperfect because it's a way of mathematically analyzing real-life scenarios. And real life is complex. There are so many variables that influence people's decisions and circumstances that it's really hard to come up with a model that will perfectly reflect real life. So what George Box was trying to get at here is that statistical models are generally very useful, and the more useful they are, the better they are. Even if they're not perfect, if they're approximating something and they're doing it reliably, then that's ideal. And the goal of any statistician is to always refine and improve the usefulness of statistical models to ensure they're as well informed and valid as possible. That's the goal with statistical analysis. To accomplish that goal, it's really important to make sure you're considerate of what it is you're analyzing, very clearly defining variables when you go to do data collection and analysis. You want to make sure that you're approaching the issue with integrity. You want to make sure that you're not interpreting it with your own internal biases. You want to make sure that you're using the tools for statistics and statistical modeling responsibly as you go towards analyzing real life situations. This is one of the more fundamental lessons of statistics. It's not algebraic in any way. There's no number crunching that goes along with this lesson. This is a conceptual lesson that I think every student of statistics should learn because it's really important and it's often overlooked if you were to go out into the world and view the sort of common understanding of statistics. So this should really be your one big takeaway, not just from this lesson, but I think from the unit as a whole.